Welcome back. In this video, we're going to be talking about conditional probability and independence. So as a reminder, we defined probability last time as P of E, the probability of an event E, is the number of elements in event E, N of E, divided by the number of elements in the sample space, N of S. And typically the number of elements in the sample space is the universal set. So if we are drawing a card from a deck and we want to know the probability that that card is a spade, the denominator would be 52. That's the number of cards in the deck. That's the universal set. And it's also the sample space for that example. However, there are going to be times where our sample space is a subset of the universal set. And so that is what conditional probability is. So let's start off with looking at an example of that. So for our example, we're looking at the 2019 U of A freshman class. In that class, the number in the universal set, there were 4,562 new freshmen that year. The number of those students who are enrolled in finite, set F, was 1,240. The number of students enrolled in English composition, set C, that semester was 1,443. And then the number who enrolled in both finite and English composition was 627 that semester. All right, so let's start off by filling out our Venn diagram. So the intersection, 627, that's going to give us our region 2, 627. And then we have region 1 and 3. So region 1 we're going to find by taking the number of students enrolled in finite, 1,240, and subtracting out the 627 students that were in region 2. That's going to give us 613 students in region 1. We're then going to take the number of students in English composition, 1,443, and subtract out the 627 students that were also in finite, region 2. That's going to leave us with 816 students in region 3. Now, we know the entire universal set should add up to 4,562. So region 4 would just be the difference between that and the sum of regions 1, 2, and 3. So if we add up all the numbers in regions 1, 2, and 3, and then subtract that from 4,562, we get 2,506 students. And so those would be the students who are not taking finite and are also not taking English composition. All right. So let's find a couple probabilities here. Let's start off with a probability that's similar to last time. So the probability that a student is enrolled in finite. So the probability that a student is enrolled in finite would be the number of elements in that event. So that would be the number of students in finite, 1,240, divided by the number of students overall, the universal set, 4,562. Now, really, this is a conditional probability. This is not the probability that any person in the world is taking finite. It's not the probability that anyone in the state of Arkansas is taking finite. It's not even the probability that any student at the U of A is taking finite. This is the probability that a randomly selected student from the freshman class of 2019 is taking finite. So we're already looking at a smaller sample set than the entire world. So what we're going to do now is we're just going to narrow that down a little farther. So let's find the probability that a student is enrolled in finite given they are not enrolled in English composition. And so the way we write that is the probability of F, and then we draw a vertical line, and then we write our C complement, the part that is given. So we want to find the probability that a student is taking finite given they are not taking English composition. All right, so if they are not taking English composition, so the given part, that's the part that's going to come after the vertical line, that's what's going to tell us what our denominator is. It's what's going to tell us the total number in our sample set. So in this case, we're saying we know the student is not in English composition. So essentially, we don't care about anything that is in regions 2 or 3. So we're going to ignore those numbers. We are removing those students from our sample set. So we want to know the probability that a student is enrolled in finite, given that we only have these two numbers left, the region 1 number and the region 4 number. So the probability that a student is taking finite out of those two things, well, first of all, that denominator is going to be just the sum of those two numbers, 613 and 2,506. That's going to be 3,119. And then our numerator is going to be the number of those students who are taking finite. And that's the 613 students who are taking finite. So the probability that a student is enrolled in finite, given they are not enrolled in English composition, is the 613 students who are taking finite who aren't also taking English composition out of the entire freshman class of students who aren't taking English composition. All right, let's look at another one. Now let's say, what's the probability that a student is not taking English composition given they are taking finite? So now we've just reversed the order. So here, the given part is finite. Now we know they are enrolled in finite, which means they are not, they are not anything else. They're not outside of the finite circle. So we can just kind of cross everything else out that is outside of the finite circle. We don't care about any of those numbers anymore. Region 3, region 4, those are not relevant to this example because we were given that the students are in finite. So now we want to find our denominator here. So our denominator here would just be the region 1 and region 2 totals, which are just going to be the total number of students in finite, 1,240. And our numerator is going to be the number of those students who are not in English composition. Well, the region 2 students are in English composition. The region 1 students are not. So that's 613. So the probability that a student is not in English composition, given they are in finite, is 613 of the finite students out of the total number of finite students, 1,240. Now, you may have noticed the given part tells us exactly what our denominator is. So in our first example, not composition, that's what our denominator is. There are 3,119 students that semester who were not taking English composition, so that was our denominator. That was our sample space. For the second example, the denominator was 1,240. We were given the student was in finite, so the denominator is the number of students in finite. So that's conditional probability. We are just narrowing down our sample set. So rather than it being the entire universal set, we're only looking at a subset. And the way I recommend doing it is just like I did here, to actually cross things out and only look at the set that you're interested in. That makes it pretty easy. So sometimes you'll be able to make things like Venn diagrams, or sometimes you'll use tables. And then there's other examples like cards and dice that will be a little bit different. But just in general, if you can make a diagram, that does make it a little bit easier. All right, so now let's move on to independence. All right, so independence, and this is an informal definition, but independence are events where the occurrence of one event does not affect the occurrence of the other event. So, for example, if we were to roll a die and we wanted to know what's the probability that it's a 3, well, that's 1/6. And then what's the probability that we roll it again and the second time it's a 3? Does that change? Well, no. If the first die is a 3, the second time when we roll the die, every probability is still 1/6. It could be a 3 or it could be a 5. All the probabilities stay the same. So if we wanted to find the probability that we get a 3 on the first roll and a 3 on the second roll, we'd multiply 1/6 times 1/6, the probability of getting a 3 on the first roll and a probability of getting 3 on the second roll, and we'd get 1 out of 36, 1/36. And if you look at the dice table we created last time, you'll see there is exactly one entry in that 36 entry table that is the die roll 3-3. So when we have independent events, to find the intersection of those events, we can just multiply the probabilities together. Now, we can also use this to test for independence. So this is the formula, P of E times P of F equals P of E intersect F. That's the probability for the intersection of independent events. So if we multiply the probability of two events together and it equals the intersection of those events, that means they have to be independent, because that means the formula for the intersection of independent events worked. So let's use that to test independence. So in this example, we're trying to find out if the events y and h are independent. So we have this table here, and people are being categorized in two categories. So this is a very common way to test for independence. And for those of you who are business majors, you will likely take a class in the near future called data analysis, where you'll learn some statistics. In statistics, there is a statistical test called the chi-square test of independence. And it's a really important test and is really, really useful. And it's going to kind of expand on what we're learning here. Mathematical independence is very strict independence. Chi-square independence is not quite as strict, but it's really, really useful. So anyway, so in this table, we have people broken down by two categories. So we have them broken down by age. So we have the younger group, 18 to 34, the kind of medium age group, 35 to 59, and then the older group, 60 and above. And then for those groups, we have people that are homeowners and non-homeowners. So we want to know, are the events y and h independent? So first of all, let's think about what that would mean, just not even mathematically speaking, but just in general. So if y and h, so that's young people and homeowner, if that's independent, then that would mean people in the 18 to 34-year-old age group are just as likely to be homeowners as people in the 60 and above age group, or the 35 to 59 age group. And so you probably know just in general that that's probably not true. Homeownership tends to be dependent on age. The older you get, the more likely it is that you will be a homeowner rather than a renter. So just in general, we can probably guess that these are not going to be independent, but we can also mathematically show that they are not independent. So let's find this out. So if these two events were independent, then the probability of y times the probability of h would need to equal the probability of y intersect h. Because again, that's our definition for the probability of independent, or the intersection of independent events. So the probability of y, well, that's going to be there are 29 people in the y group, the younger group, 29, divided by the total number of people, which is 100. And then the P of H, so that's the probability of being a homeowner. So there are 60 homeowners out of the total of 100. And then we're going to see if that's equal to the probability that y intersects h. So y intersect h is where those two things literally intersect. Y intersect h. And so that, of course, is the 7. The 7 younger people who are homeowners. So that's 7 out of 100. Okay, so you'll notice none of these are conditional probabilities. So we would multiply 29 out of 100 times 60 out of 100. That's going to give us 0.174. And then 7 out of 100 is 0.07. And of course, those numbers are not equal to one another. So the answer to this question, are the events Y and H independent, is no. So just like we kind of figured, home ownership is dependent on age. All right, let's look at one more example. In this example, we have people broken down by the same age groups. But in this case, we have, are they a new customer or a returning customer? So the idea here is this is a survey given, or not necessarily a survey, but this is data that a business has where they have tracked orders, and they have created this table based on whether an order is from a new customer or from a returning customer. So new customer is in, returning customer in complement. So we want to know, are the events M and in complement independent? So M is the age group 35 to 59, and then in complement is returning customer. So what would it mean for these two things to be independent? Well, just outside of math, for those two events to be independent, it would mean that people in the 35 to 59 age group are no more likely to be returning customers than people of any other age group. So that would mean that people of all age groups are just as likely to be new customers or returning customers. So let's check it out. So for these to be independent, then P of M, the probability of being in the medium age group, times the probability of being a returning customer in complement, that would need to equal the probability of M intersect in complement. So the probability of M, that would be everybody in the M group, that's 45 out of 100, times P of in complement, that would be 80 out of 100. And then M intersect in complement, so M intersect in, again, M intersect in complement, that would be where they intersect, and they intersect at the 36 people who are in that age group who are returning customers, so 36 out of 100. And so then we multiply 45 out of 100 times 80 out of 100, and we get 0.36, and 36 out of 100 is also 0.36. And so these events are independent. So our answer here is yes. Those events are independent, which means that returning customers are just as likely to be in any age group, and vice versa. People in any age group are just as likely to be returning customers as new customers. All right, now let's step backwards real quick. We can also use tables like this to calculate conditional probabilities. So let's do that. Let's use the same table where we have our new customers and returning customers to find the probability that a customer is a new customer given they are 18 to 34. All right, so we're given they're between the ages of 18 and 34, so we know they are in group Y. And that we don't care about anybody else. We are only looking at group Y because we are given they are in the 18 to 34 age group. So the probability that they're a new customer, well, there are 35 people left that we haven't crossed out that are in that age group. And 7 of those 35 are new customers. And so that's our probability, just 7 out of 35. So given that a customer is 18 to 34, that's 35 people, what's the probability that they're a new customer? Well, that's 7 of those 35 people. That's it for today. I will see you next time.